Hello, my name is Matthew Smith, and welcome to my USRA project on the synthesis of allyl, anthyl, and naphthyl sulfenates. My work was performed for the Department of Chemistry at the University of Guelph under the tutelage of Dr. Adrian Schwan. To understand the big picture of my project, we must first look at a concept known as chirality. Chirality is a property of asymmetry that when applied to an object means that the mirror image of the object can't be superimposed onto the original object. That may be confusing to understand, so take a look at your left and right hands. They are mirror images of one another. And however, no matter how hard you try, you find that you cannot get both of these objects to be superimposed over one another. This is what makes them chiral. Chiral objects can be found in all aspects of life, but have especially important roles in the fields of chemistry, medicine, and biology. Chemical compounds, drugs, and amino acids are all examples of important chiral compounds that one can find in these fields. You may be wondering how chirality can actually have an impact in day-to-day life. Have you ever heard of the drug known as thalidomide? Thalidomide was a drug commonly prescribed to pregnant women throughout the 1960s in order to treat morning sickness. However, what was not known was that the two enantiomers, or two different versions of the chiral compound, had vastly different side effects. Where the R enantiomer of the drug was effective in treating morning sickness without any major side effects, the S enantiomer caused horrible deformations in the babies of pregnant women who took this drug. This is a result of the fact that enantiomers of chiral compounds can have vastly different physical, chemical, and medicinal properties. For example, ethambutol, a tuberculosis medication, is completely harmless if the SS diastereomer is taken. However, if the RR diastereomer is taken, it can lead to blindness. We can also see this in natural compounds such as amino acids. In alanine, the S enantiomer is commonly found in organisms where it is used for protein synthesis. However, if the R enantiomer is found in an organism, it cannot be used for any purpose. It is evident that understanding chirality is key to understanding both chemistry and biochemistry, and is the crux of this project. To understand the background of this project, I need to explain what sulfenates are. Sulfenates represent an important class of sulfur compounds that are chiral molecules and can also be used to impart chirality on non-chiral substrates, which is very important in medicinal chemistry. On the top, we see that sulfenates can be generated when a sulfoxide, the compound on the left, is treated with either base or nucleophiles and contains an SRG, or a sulfenate-releasing group. This then results in the formation of the ambident nucleophile known as a sulfenate. An ambident nucleophile is a nucleophile which has two centers of nucleophilicity, in this case being the sulfur atom and the oxygen atom. The mechanism for generating sulfenates depends on the sulfonate releasing group found on the sulfoxide. On the bottom of the screen, you can see two common sulfonate releasing groups, one being the trimethylsilyl group and the other being the methyl ester group. Now that some of the background of this project has been covered, we can focus on what the actual aim of the project was. One goal of this project was to both discover and perfect a synthetic method for accessing anthyl and naphthyl sulfenates, which could then be probed for their diastereoselective ratios, or basically what percentage of an enantiomer they form when they react with an electrophilic substrate. The second goal of this study was to optimize the synthetic conditions for producing allyl sulfonates. Now we can begin to look at the results of the project. With the generation of anthyl and naphthyl sulfenates, much of the project has been spent trying to identify ways to access aryl sulfides that can then be built to their corresponding sulfenates. Currently, the two methods that have had the most success involve beginning with a lithium halogen exchange on the aryl starting material. From this, we've found that the two different methods that present good possible pathways include utilizing sulfur to generate a thiol, which can act as a nucleophile to become a sulfonate starting material, or using trimethyl borate, which can then undergo chain-lamp coupling to eventually generate the same sulfonate starting material. Further work must be done to optimize these two pathways. However, the results do look promising. For the allyl sulfonate portion of the project, the main focus has been testing various fluoride anion sources in different conditions for sulfonate generation. The mechanism of the reaction has also been probed due to interest in formation of a potentially double anionic species. Also, due to the expense associated with generating the TMS sulfonate, more work is going to be put into generating and optimizing the methyl ester sulfonate precursor. future considerations and work associated with the project, the main focuses should be possibly developing a method for generating anthrol sulfides that do not require lithium-halogen exchange, as this technique produces low yields of the aryl sulfides. Of course, actually producing the sulfonates and probing their diastereoselective ratio is also a major step in both projects, and could be the basis of a very intriguing study. Finally, different allyne substitutions with various electronic groups that could affect diastereoselectivity should be probed for the allyne sulfonate project. Now that my research has been presented, I'd like to acknowledge several key players who allowed me to be successful in this project throughout the summer. I'd like to thank the University of Guelph for allowing me to perform this USRA. I'd like to thank the Schwan Research Group and its current members, Dr. Adrian Schwan, Eric Nickel, Adam Riddle, and Brendan Fay. And I'd like to thank NSERC for providing funding for this project. Thank you.